Curious about how quantum mechanics shapes the tech we use? Today, we'll dive into the mystery of Zener tunneling in semiconductors. And here in action, we see a Zener diode put into a circuit board. And guess what? These things are in great study in semiconductor physics or condensed matter physics. Today, though, we have two questions. And we're going to start off with 9.3, which is more of a what is the theory, where is it applied, and why is it useful? So we're going to use the equations to calculate the approximate transmission probability for a particle of energy E that encounters a finite square barrier of height V0 greater than E and width 2a. Compare your answer with the exact result, problem 2.33, to which it should reduce in the WKB regime where the tunneling coefficient, or probability rather, is much less than 1. And this will be very important to hang on to because we're going to need that. Now, in 9.5, where we actually have something fun to deal with in the application sense, is Zener tunneling. And in semiconductors, an electric field, assuming it's large enough, can produce transitions between energy bands. Now, for those who have never seen semiconductors, this is the band gap theory that we touched on a couple chapters ago, where we need to be able to jump from one energy level to the other because that's what's required to move. And that's what semiconductors have been making breakthroughs year after year in. A phenomenon known as Zener tunneling will happen. A uniform electric field E, which is equal to negative E naught I, so we're just putting a direction on it, for which the perturbed Hamiltonian is equal to negative E, the electron, E naught, X, so we have the energy term here and a position for the energy. And then we see this makes the energy band position dependent. That'll become a problem here soon, as shown in figure 9.7. It is then possible for an electron to tunnel from the valence, or the lower band, to the conduction band, or the upper band. This phenomena is the basis for the Zener diode, treating the gap as a potential barrier through which the electrons may tunnel. Find the tunneling probability in terms of Eg, so the energy of the gap, and E naught, as well as M, H bar, and E. So we have our work cut out for us here, don't we? And this is why we want to take a look at what this method is and why we care. Clearly, in Zener tunneling, the potential barrier is not constant, but rather has a slope due to the electric field. And this is what makes the WKB method particularly effective in calculating the tunnel probabilities. Because the system, the potential varies gradually with position. As such here, we have the case where it's a sloped energy barrier in the Zener tunneling. So very cool. But because we're bringing up old topics, what happens when we look at, what kind of semiconductors do we have? What are the two types? Okay. Now, again, band gaps, there's different ways to get things flowing. So that's a little hint there. But don't forget the PDFs. Comment for the PDF because it's been weird linking on YouTube lately. I'm not sure why, but the PDFs are still available if you want them, although most of what we're going to cover is in the actual video. But in case you want them for your archives, feel free to comment and I'll send them your way. But let's dive in because this is going to be fun. Okay, so stop one here. We have to take a look at what the potential is. And this is the potential that we made back in question 2.33. Now notice that in 2.33 we used something where we had where we used the coefficients of the solution types, exponentials here, traveling wave there, some function inside, and then another exponential traveling out, and we took the ratio of F to A. Okay. Here though, what we're doing is slightly different. Instead of the line being here, we push this to the axis, and we just extend this down to 2A. So slightly different, but not too bad. So to put that in mathematical terms, the potential is now V naught, which is from 0 to 2A. And again, all of this is question 9.3. And so because of this, we have to use the magnitude of the momentum here, since our E naught is greater than our E. And some books denote it as the non-classical, since this is the non-classical region that we saw in the last video. What's cool about this though is that you could switch the sign because all we're concerned with is the magnitude. So simply switching V naught and E is fine. Um, Notice that on the outside, the V is 0, so we're good there. On the inside, we just have some value. But since we're interested in tunneling, the only region of interest is inside the barrier. And from that, we can go ahead and find the potential from that. And if you're following along in the book, we clearly see that the momentum is defined in equation 9.2. So feel free to grab that while you're at it. Okay, so thankfully now we can use the equation 9.23, which gives us the tunneling probability in terms of gamma and an exponential. So we just take the integral of the momentum over the space we're looking at. In this case, that's 0 to 2a, so we're fine. Everything in here is just the magnitude, so we're good to go because everything in here is a constant with respect to x. It can come outside. And then we integrate over dx, which just leaves us with 2a minus 0, or just a factor of 2a. Pretty easy there. So we plug this in. We see this is what we get for the tunneling probability, and we're fine and good to go. But if we want to compare this to the exact answer, which we found in problem 2.33, here's what we had. Okay. Now, what's interesting here is that sinh and the exponential look far away, but there's actually some quick cunning stuff that we can think of. The WKB method works where the barrier is very high and or very wide, which is to say that the probability of the tunneling is small. Remember in the question statement it said t was much less than 1. So because of that, we know that gamma has to be large if we're going to have an exponential. And because it's a negative exponential, gamma being large will make sure that that probability is small. So we're pretty cool. We're good to go there. And then as far as the sinh is concerned, we can use exponentials to simplify. Let's see how we do that. So since sinh is defined as sinh of gamma is defined as E gamma minus E of negative gamma over 2, remember in here that gamma has to be very large. So if gamma is very large, this E to the negative gamma goes away. That's what we're after. And so this simplifies down to E gamma over 2. And if we square that for what we have inside, we're good to go. The reason why we use gamma here is because when we look back at the sinh in the last term, we saw that it had the same argument as what we found the gamma was for this case. So very cool. It's a very cool substitution that works handily. But nonetheless, we break it up and we see what we're doing here. And so this turns into the exact result into the approximate result, which we see here. We plug the exponential in. Now, because this is an approximation, this one here doesn't really do us much because of the exponential here. So we can get rid of that. And then we see that we just have 1 over double fraction here. So we multiply by the reciprocal and we're fine. But we put a negative sign here. And what we see here as far as this leading coefficient term here is that the dependence on E in the leading coefficient is of smaller order compared to that of the exponential from gamma. So in the scope of thinking, we can reproduce the WKB approximation result because this thing we'll just say has order 1 since V is much bigger than E. Okay, so we'll just put that to 1, which we do in the curly brackets, and we see we get negative 2 gamma, which is exactly what we expected out of the WKB result. So we actually get what we're actually looking for, which is completing problem checkpoint 9.3, and we are good to go. Now we can move on to the application, which is going to be a lot of fun. So, before we can do anything in this stop, what we have to go back is look at the figure 9.7, which touches on the energy band, right? And what we could say here is that without the electric field, we're flat. Normally, we just have a general energy gap here, hence Eg. But with the electric field, we see that it turns into a slope. And the potential energy barrier in the Zener tunneling has a downward slope due to the electric field applied across the semiconductor. The electric field, E0, modified the energy bands, making them position dependent. So, position dependence, we can go ahead and use the WKB method, and as a result, the energy barrier between the valence up here and the conduction bands becomes sloped with the slope defined by the electric field. Okay, so let's see if we can put that into another graphic. So if we hold the lower band at some level E, and then we see that we're starting up top, we slope down as we saw from the figure, we can go ahead and say that this E and E are the same because we have to be at some level. But then we have the band gap here, which raises this, and then the energy level decreases it down, so we're good to go. And what we could say is that when calculating the tunnel probability, we treat the energy barrier, which separates the valence band from the conduction band, as a quantum potential that has an electron that the electron must tunnel through, and the slope of this energy barrier induced by the electric field reduces the effective height of the barrier over distance. And that's what is going to facilitate the tunneling. So, all that word mashing now leads us to, well, this approach tells us that we need to consider all the energy contributions by the electric field, and that forms this potential here. So very cool, because we see that the band gap on the lower end is less than the potential, which is that line above it. We know that we're in the non-classical region here, so we need to be able to use some of the methods from WKB and their regions. And so we use the modified momentum here, so we just use the magnitude. And we see that if we plug it in back and do equation 9.2, we see that the E cancel because all we did was raise everything by a factor of E, so canceling out makes sense. And then we see that we get this negative sign that tunnels out through, no pun intended. But because we're in the magnitude, we can go ahead and take the negative sign as an I and simplify. So factor that negative sign into an I, but because the magnitude of I is just 1, we can go ahead and split up the radicals as we see here, and we're good to go. Now, if we assume that the electron energy E is at the bottom of the conduction band, at the top of the valence band, and vice versa, the barrier V of X is approximately Eg. So if we're just taking that out, then we see that Eg is the top band that they're trying to reach. And so when we're looking at this, we're going to have turning points to consider, meaning that wherever the potential is actually equal to the overall energy that we would have above it, or actually equal to it, we see that it happens at one point. And we saw on the graph that the E level intersected the Vx level at one point, and that point would be at Eg over E, the electron, with the electric field. And we see the algebra that proves that. This happens at point A, but point A has this as its definition, so we'll be good to go. And defining these turning points is going to be very crucial and critical, especially when we look at the connection formulas. So be aware of that. The harmonic oscillators are coming back, and we'll see how that is done in a more thorough manner next time. But be aware, this is how you determine the bounds on the integrals, which we will see need to be evaluated now. So, referencing our old handy equation, 9.23, we see that we integrate from 0, the start of the barrier, to the intersection point, or so the length that the electron would have to tunnel through. And then we see that since it's the magnitude of the momentum that we're integrating, root 2m is a constant, so we bring it outside. And we see that now we actually have an x dependence. So that's pretty cool. And so if we let u equal everything inside the square root, then our dx here, once we go ahead and take the derivative of both sides and simplify, is the negative 1 over e0 du, so we're fine there. While we're here, so we don't let the sub back in, we'll just change the limits. So plug in the top limit here, cancel, then eg and eg cancel, so we get a 0. Fantastic. Then we're stuck with u at 0, which is eg. Okay, that makes sense. The difference between E and E is EG in the initial setup. Makes perfect sense. And so if we plug these in with the substitutions, EG on the bottom, 0 up top, we have a negative sign from the du. This means that we can go ahead and get rid of the negative sign by switching these two limits, and we can go ahead and pump out this integral pretty fast. So we go ahead and switch it. Put the integral up to, or the integrand to a power instead of a radical, and we see that we add 1 to the power, divide by the new power, then evaluate. When we do that, it's pretty simple. Just plug it in. We see that 0 goes away. So if we plug this into the tunneling coefficients, we actually get something really awesome, which clearly here, T would equal this, and we're good to go. And thus we see that we have all of it put together. And that's very, very tidy and very, very neat, all things considered. But again, this assumes that tunneling probability is very small. So the energy gap here having a big play with the cube right there, even with the square root, very big on it. And yeah, this is going to be something that will keep coming back over and over again. So we have successfully completed both problems, and now we can move on to the concluding remarks and touch on some of the fun stuff. So while we kind of skirted through a lot of that on the mathematics side, because there wasn't that much necessity, we were able to talk a lot about everything in terms of the setups and why the setups work, why they're important, things of that nature. So I was very happy with that. Um, Again, I have to thank everybody who supported this, whether it's through Buy Me a Coffee or Patreon, because now that we're getting into a little deeper territory in the book, the support is definitely needed for the fact that it takes up more time to produce this stuff. So thank you, thank you, thank you. If you're in the broadcast channel, which I might just make a Discord server, I don't know, let me know what you think. Um, I keep sharing resources I find as I complete these things. So that might be nice for you to have, especially with some of the tables, charts, and databases that we need it for 9.4 with the nuclear effects. So keep that in mind. Books, notes, and other reference materials will be found wherever I can put them. If you have any questions, please feel free to reach out. And as always, thank you for watching. Until next time, stay curious.